Hello everyone, good morning. I'm Neuza and I come from the University of Tras-os-Montes, Alto in Portugal. And I'm going to present the work developed with two professors, Professor Paulo and Professor Neuza. The title of the work is Subtractive Mountain Clustering Algorithm applied to a chatbot to assist elderly people in medication intake. Okay. So this work has been motivated by so many mistakes made by the elder people when taking medication. Elder people often take their medicines at the wrong time as well as the wrong dose. It is also frequent that they confuse the pills. This is easy to happen since they tend to take many different medicines per day. In face of this, the question is, how can you help in sorting this mess? How can you combat these medication errors? You started looking for a solution, and the crucial seems to be they stay somehow more closer to their prescriptions. After reviewing several solutions, as example, an automatic medicine dispenser and several smartphone apps, we found that the chatbot is a possible solution to avoid medication intake errors. The aim of this work is to develop a chatbot to communicate with the elder using natural language. The proposal is to use the Subtractive Mountain Clustering Algorithm, SMCA, to process natural language. I'm going to talk about the medication errors, then about chatbots and natural language processing. I'm going to explain the Subtractive Mountain Clustering Algorithm, SMCA, and apply it to a case study. And finally, I'm going to talk about conclusion and future work. The use of medicines in treating diverse diseases is becoming more and more popular. Therefore, the medicine intake has been increasing, adding up the fact that with the advance of age, we are prone to accumulate different pathologies and the associated treatment. We note that the average old person takes several medicines per day. Therefore, the probability to make a mistake in their medication is high. A study carried out in the United States in the period 2010 to 2011 showed that almost 90% of the older people take at least one prescription drug, and 85% take at least two, and 36% take at least 5 prescribed medications. As I mentioned previously, we find the chatbot as the solution to combat medication intake errors. It simulates a conversation with a user in natural language, and it is designed to respond to a user request. Frequently, it is an artificial intelligence software. There are many algorithms behind chatbots, and this can be included in 3 categories: unsupervised, semi-supervised, and supervised learning. Chatbot should be able to questions about physician prescription, like questions about dosage, timing, duration. It will also be able to give information about the drug package insert, like what is the medicine for, side effects, indication, and posology, etc. Another extra information is related with the box color and pill color. The processing of the natural language is a crucial step in the achievement of a functional chatbot. This area of artificial intelligence supplies the computer with the capacity to understand human language by transforming words into numeric entities understandable to computers. Then, machine learning techniques can be used by the latter. The user poses a query to the chatbot, then through natural language processing the most relevant information to the query selected in order to supply an adequate answer. For natural language processing, it takes a few steps before applying the subtractive mountain clustering algorithm. They are splitting into paragraphs, tokenization, pre-processing, and finally word embedding. I will discuss them in the following slides. The first step is to divide the text into paragraphs. Every paragraph is said to be a document. We use the package insert of the medicine share Alto to make an example. Next, every document is converted into a tokenized structure. This is every word, number, or symbol is a token. A token is a chain of characters. After you get the tokens, we do some steps related to preprocessing. We remove the stop words. This is a function of MATLAB to do this, where words list is predefined. After, we remove the unnecessary punctuation and number, and I said unnecessary because we did not remove the punctuation that appears in the ends of a sentence, because it is necessary to define where sentences end. Then we normalize the words to reduce words to a root form. Therefore, we reduce them to their dictionary forms, once again using a predefined MATLAB function. Finally, we eliminate the words of low relevance, and these are words that appear less than 3 times and words that have less than 2 letters. To finish, the remaining tokens are converted into numbers. From here on, the chosen algorithm to process the language is applied. Now let's see the subtractive mountain clustering algorithm. The algorithm is used to fulfill the needs of natural language processing as the subtractive mountain clustering algorithm. The algorithm was introduced by Xu in 1994 and claims that enormous datasets are partitioned into subsets called clusters, and each cluster is represented by one element, a cluster center. We used this algorithm to define word sets, the clusters. The center of each cluster is calculated by this function, where the potential of every word pair is evaluated. The potential of the pair of words R and S is equal to this factor B, and this factor B is related to the number of times each pair appears together in same sentences or paragraph, multiplied by this sum, where this n is the number of words. This alpha is equal to 4 divided by the square of R sub A, where this R sub A defines the data point's influence. And here you have the square of the distance that words appear in the package insert. This distance is calculated by these three ways. In the first case, if two words are in the same sentence, the distance reflects the number of words that separate them. The end of the sentence recognition is done by punctuation marks. Second way is that if two words are in the same document but in different sentences, the distance reflects the number of sentences that separate them and the number of words. This C sub n is the number of separation sentences, and this A is an hyperparameter that is adjustable according to the average number of words in each sentence. And finally, we have the third case, that is if two words are in different documents, or this is in different paragraphs, the distance only reflects the number of paragraphs that separate them. This P sub n is the number of separation paragraphs, and this B is another hyperparameter adjustable according to the number of sentences of each paragraph. Thus, we are able to obtain the potential of every word and choose the one with the greatest potential as the center of the first cluster, and define the other words cluster using this center. After the potential of every distance has been computed, as the matrix D is symmetric, we sum up all the potentials for each word, and you obtain a vector with n columns. Thus, we are able to obtain the potential for every word and choose the one with the greatest potential as the center of the first cluster. After calculating the first cluster center, we calculate a new potential for each word pair using this expression, where the new potential of the word pair R and S, where the new potential of the word pair R and S is equals to, let's start now. Where the potential of new word pair R and S is equal to the previous potential of the word pair minus the potential of the first center of cluster multiplied by this factor B, multiplied by this exponential, or where you have a beta. This beta is an adaptation of this alpha. And here we have the distance between the first word cluster to others. Each time we select the center of the next cluster, we revise the value of the potential. Finally, we calculate the belonging degree of each word to the cluster using this equation. The belonging degree is equal to the inverse of this sum, where R is the word and S is the cluster center. This M is the fusification parameter that controls how fuzzy the cluster is. After applying this MC algorithm, you can group the words defining clusters. After defining the clusters, we can calculate the belonging degree for each word to a cluster and relate the words. Now, let's see a case study where you apply the SMC algorithm to the package insert to Alto. We obtain 297 documents and 838 tokens. The figure shows the number of times the first 40 most frequent words appear. The most frequent word is the name of the drug, Alto, and the second is patient. After the first 10 words, the frequency of each expression remains approximately the same. After applying the word relevance matrix, we get 468 relevant words, represents 55.85% of the total words. Here is the distance between relevant words is represented. On each axis, we have the index of the words. And the closer to white the color, the smaller the distance between words. This image was used to verify if the distance were being calculated correctly. Here are the 20 clusters we find. In the graphs, the belonging degree is also represented. Here we have the 40 words that have a degree of 1. In addition, we calculate the degree of belonging of each word to the cluster, and here we have the graph that shows the number of words belonging to each cluster, with a degree of belonging greater than 0.5. The first cluster have 85 words associated, and the second have 55 words associated. We can get the most significant words with question pair processing and associate them to a cluster or set of clusters. The answer is in accordance with the belonging degree of the words to cluster. For example, one question with the stemming words risk, fatal, and bleed, like an example is, what are the risks of a fatal bleeding? This question has multiple possible answers because these are words that belong to different clusters. So we can sort answers by the relative relevance. And this relative relevance is calculated according with the belonging degree of the words to a cluster or to a paragraph. Answers correspond to the paragraphs whose profile of belonging to the words in the question and the document are closest. The answer with 1 of relative relevance is this: Alto increase the risk of bleeding and can cause serious or fatal bleeding. So we conclude that chatbots have potential to help elderly people intake medication, especially if they can emulate human conversation. And a chatbot is proposed as an system to help elderly with medication intake. A fundamental step to enable communication between users and chatbots is the processing of natural languages. We adapted the Subtractive clustering algorithm to natural language processing. To the best of our knowledge, this algorithm has not been used before to resolve this type of problems. The SMCA does not define the number of clusters, leaving more freedom to the association. Instead, through word cluster creation based on distance, we are able to define a degree of belonging among words and thus build an adequate answers to the posed queries. As outcomes of the work, we have that learning about chatbots and natural language processing, we reviewing the state of the art of the problem in question, an aid system to help other people with medication intake. We propose a solution, a chatbot, able to interact with the user in natural language. We make the application of the SCMA to define a relationship between words. We implement the proposed algorithm and apply to a simple problem, obtaining the results that we consider promising. As future work, we pretend to build an interface, to refine the algorithm, to study the accuracy of the algorithm, research other algorithms to solve the same problem, and to study the adherence of people of more advanced age to chatbots. Thank you for your attention. Any questions?